Good afternoon. So in this lecture I will describe the experimental methods to measure the energy in particle physics. So this lecture is divided into 3 modules as usual, and at the end of each module you will find some questions, and at the end of the 3rd module you will also find some homework. So these lectures actually draws a lot of material from these 3 references which are listed here. And so to start with, we have to analyze at first what are the processes which are relevant for the energy measurements. So in order to measure the energy of a certain particle, this particle has to release its energy in your detector. So your detector will detect the energy released by the particle, and it will then convert this energy release into a signal, and from this signal one has then to come back to the original energy of the particle. And the process, so let me start with the Bremsstrahlung, which is a fundamental process for a charged particle of a given mass and a given charge. This is deflected by the nucleus, and during this deflection, so since its speed is changed, so this means that there is an acceleration, and so whenever a charged particle is accelerated, then it emits some radiation, which is called Bremsstrahlung. So this process of emitting radiation is called Bremsstrahlung process and Bremsstrahlung radiation. So the scattering, the elastic scattering of a particle off the nucleus is given by this formula, where you see that there is the sinus of half of the emission angle to the 4th power at the denominator. So this means that, of course, this cross-section is very large when theta gets very small. So this tends to be forward, the particles. And indeed, there are here listed on the left several formulas showing in more detail this behavior of the cross sections, and so once you have described this cross section of the process, then you have the emission of radiation, which is indeed described by Maxwell equation. And so this emission of radiations means that this is done at the expense of the initial energy of the particle, which loses its energy due to this radiation. And so the energy loss here is reported in terms of dE over dx, which means energy loss as a function of the transverse of the traversed material. And you see that this is the formula here gives you the typical behavior of this energy loss, which is somehow proportional to the density and to other there are other important behaviors like the z square and of the nucleus and the z of the particles itself. So if you do this the same thing, but in terms of accounting for quantum mechanical effects, then you end up with a slightly different energy loss dE over dx curve, where again you see that the main features are the following. It is proportional to the square of the atomic number of the material. It is inversely proportional to the mass number of the material. It is proportional to the fourth power of the charge of the incoming particle, and it is also proportional to the density of the material. It's inversely proportional to the squared of the mass of the incoming particle, and it is also proportional to the energy of the incoming particle. So then you see that given all that, this can be put into the form of an exponential, where this exponential is somehow is a function of this x0, which is called the radiation length, and so this gives you the behavior, the exponential behavior, and it characterized what is the typical length in a certain material where the energy is decreased to about 37% of the initial energy. Indeed, you see here that x0 is proportional to the square of the mass and to the mass number of the material, and then it is inversely proportional to the raw density, to the fourth power of the charge of the incoming particle, and to the second power of the atomic number of the material. So this radiation length is indeed as an important, a very important parameter to indeed describe this energy loss in a certain material. Then all this indeed depends on the mass of the particle, and this brings us to the definition of the critical energy. So indeed you have an energy loss process which depends on this electromagnetic interaction of the particle with the nucleus. But then so first of all, this is an electromagnetic process. The basic force which is behind this energy loss is the electromagnetic force, and therefore, I mean, then we will discuss other kinds of force and other kinds of mechanism for energy loss. But then what you see is that given this kind of process, the emission of radiation, this Bremsstrahlung, which is induced when a charged particle is accelerated, so this is a typical electromagnetic process, this process depends on the mass of the particle. So for instance, if you take a muon which is a kind of twin partner of the electron, but with about 200 times the same mass, then they have very different, they both experience, I mean both the electron and the muon, they do experience electromagnetic interactions, but the energy, which is the so-called critical energy, the energy where the Bremsstrahlung starts to be dominating with respect to the ionization loss, the energy loss by the ionization process. This critical energy where you start to have the Bremsstrahlung dominating, starting from this threshold, your Bremsstrahlung energy loss for the Bremsstrahlung will be dominating with respect to the ionization. This critical energy is very much different, and it very much depends on the mass. In particular, for the you see that for the electron in traversing copper material, this energy is about 20 MeV. For the muon, this is about 400 GeV. So it's very much different. So, which means that this Bremsstrahlung process is much less important for muons than for electrons. And since all the other particles, charged particles, they are all heavier than the muons, and then the electrons, of course, then this Bremsstrahlung process is by far the most important process for the electron, and it is, let's say, to some extent relevant for muons, but at energy much higher, and it is not relevant for other, less and less relevant for other particles, because as you will see, then these other particles, they also experience other kinds of interaction, which will produce different kinds of energy loss. So then if you consider energy ranges where this 400 GeV is possible, this is and above 400 GeV, then this is certainly the domain of the LHC. So then, and it is also the domain of cosmic rays experiment, where you have very high energies of cosmic rays, and so both at the LHC and in cosmic ray experiment, the Bremsstrahlung for electrons and also for muons can also be relevant. So not only the Bremsstrahlung for electron, but also the Bremsstrahlung of muons can be relevant in this context, in the context of cosmic rays and the LHC experiment. While the electrons, it is essential also at much lower energies. So here you see what happens. I mean, if you don't start from an electron, but if you start from a photon, then the photon, when it will interact with the nucleus, it will produce a pair, an electron-positron pair. And this diagram is indeed very similar to the electron Bremsstrahlung, so there is a crossing symmetry. So this means that basically you compute the cross-section in the same way. And so one can actually define, by using this, you compute what is the typical energy loss for a photon as a function of the traversed material, and indeed you end up with a similar exponential behavior of the initial energy, which degrades with an exponential, and the constant in the exponential is not anymore the radiation length, but it is it is called lambda here, and it's very much similar to the radiation length. It's 9/7 of the radiation length, so it's very close to the value of the radiation length. So let's say only about 30% larger. So then this is clear, it must be of the same order of magnitude, because it is still the electromagnetic process, and even the Feynman diagram of the process is very much very much the same as for the electron Bremsstrahlung, but it can be slightly different due to the fact that there is you start with the photon, and then you end up with 9/7 of x0. So if you put all what we have seen together, both the way the electron propagates and the way a photon propagates, so, and somehow if we assume that this 927 is not very far from 1, so what you have is that actually you can divide your traversed material into steps. Each of them is one radiation length. So you have here one radiation length, another radiation length, a third radiation length, and the fourth radiation length. So this is, in this schematic drawing, there are 4 radiation lengths of the material. So, and then you have a photon in the top part and an electron in the bottom part. So then the photon will propagate, and after about 1 radiation length it will turn into an electron-positron pair. Both the electron and the positron, after on average 1 radiation length, they will produce another photon. They will Bremsstrahlung, produce another photon and another electron. And this is the same for the electron in the bottom part of the picture. So you have the electron, after 1 radiation it will produce a photon and an electron, and the electron will produce another electron and a photon by the Bremsstrahlung. The photon will produce an electron-positron pair, and so on. So as a consequence of that, we know that every x0 you have typically a degradation of the energy by a factor which is 1/e, and you have a multiplication of the particles, because then you start from 1 electron, you end up with an electron and a photon after 1 radiation length, and so on. And also with the photon you end up with 2 electrons, and then from each of these 2 electron positrons, then you end up with another couple of pairs for each of them. And so in summary, what you can say, that after n times radiation thickness, which is n times the radiation length, then the number of particles you end up with is 2 to the power of n. And also the average energy of this particle is E0, the initial energy, divided by the number of particles, which is 2 to the power of n. So this process, or this shower development, it is called the shower development because you see it from the diagram that I have shown before, that this is really a shower. It develops like in a tree. I mean, you have the different branches, and every step it multiplies by 2 the number of particles. But this shower development stops when the energy of the particles becomes as low as the critical energy. So below the critical energy there will be no more Bremsstrahlung, and so there will be no more shower development. And so if we can compute the maximum number of radiation length in a certain material given as 1 over the log of 2 times the log of the ratio between the initial energy and the critical energy. So the critical energy depends only on the material, and then this tells you that the typical length of a shower increases with the logarithm of the initial energy, which is a property very interesting because this means that you can somehow confine your energy in relatively short material, even at energies which are very high. And so then you can count the number of particles after a certain at the step number n. You have 2 to the power of n, and so you can measure the total track length of the segments. So this is proportional to the radiation length, and you have to sum up all these track length by each particle, and this is indeed, if you make this if you sum up these quantities, which is 2 to the power of n, then you end up with this well-known formula, which is which gives you at the end, if your initial energy is much higher than the critical energy, this is about twice the ratio between the initial energy and the critical energy times the radiation length, which means that the total track length is proportional to the incoming energy. So the total track length is proportional to the incoming energy. So, and this is the calorimeter principle. So if you measure the total track length, this is proportional to the particle energy. And so with a certain calibration function, which is supposed to be linear, then you get, starting from the measurement of the track length in a block of material, which is then the track length can be also estimated by the number of heats and the charge that is somehow released in your detector, the charge which is collected, and after the interaction of these particles when they cross your detector. So in some sense there are different ways of collecting signal which is related to the tracks, to the track length of each individual particle inside the shower. And if you sum up all these signals, which are somehow related directly or indirectly to the track length of each particle, then you end up with a signal which is proportional to the incoming energy. And this is the principle of calorimeter. So you essentially absorb all the particles, and you do the energy measurement by the total absorption of particles. This shows you, this schematic drawing shows you the difference between a muon, which somehow can be absorbed in the material just because you have enough material to stop it, but it will not shower unless its energy is extremely high, as we said in the beginning. Then the electron will interact with the absorber and will produce a shower, and the same will be done by the photon. And so at the end, when you compute your track length in this shower, you basically have to count all the particles which are produced in the shower. So in the calorimeter they ionize and excite the material. So in the ionization you produce electron-ion pairs, in the excitation you produce photons. And so if you measure the total number of electron-ion pairs and also the total number of photons, this gives you the particle energy. So you can either get the signal from the ionization or the signal from the excitation, and then this total number of particles, this will be proportional to the incoming energy, which means that your uncertainty on the energy will be driven by the uncertainty on this counting, on this number. So it's a counting method, so it is driven by the Poisson statistics, and therefore you expect that your energy resolution, I mean your relative energy resolution, delta E over E, this is delta n, the uncertainty on the counting, on the number of the total number of particles that you detect, divided by the total number of particles itself, and this goes with 1 over square root of n, which means that somehow, since n and the energy are proportional, this is a certain factor divided by the square root of the energy. So this is it's a very important point, because then you see that the energy resolution, the relative energy resolution, goes as 1 of square root of E, which means it improves at very high energies. Electrons and photons, they show electromagnetic cascades, both at the GeV and TeV energies, while strongly interacting particles like pions, kaons, they produce hadronic shower in a way which is very similar to the electromagnetic cascade, but this will be described when we will see hadronic calorimeters. So then the way you can actually collect a signal is can be different. So you can collect when you produce by the ionization of the medium, you produce electron-ion pairs, then you can collect the charge which is produced, and you measure the charge which is collected after this ionization process. The other way is that you can somehow be sensitive to the excitation mechanism, and so you can measure the photons which are produced by the collision of the electrons with the atoms of your material. And then you may have scintillating crystals, plastic scintillators, which can somehow detect these photons. And so the total amount of pairs in case of ionization signal, or photons in case of measuring this photon yield, is proportional to the total track length, and it is in turn proportional to the particle energy. So in summary, calorimeters are blocks of instrumental materials where the particles are fully contained and they are fully absorbed, and their energy is transformed in a measurable quantity. The interaction of the incident particle with the detector produces a shower of secondary particles with degraded energy. The energy deposited by the charged particles in the active part of the calorimeter, detected in the form of either charge or light, provides a measurement of the energy of the incoming particles. So The calorimeters can also be classified into electromagnetic calorimeters or hadronic calorimeters, whether they measure the energy of electrons and photons, or whether they measure the energy of hadrons. So the construction can actually be classified into two categories: homogeneous calorimeters, which are built of only one type of material that actually performs both the energy degradation, so it acts as the medium where the particles interact and shower, and it also acts as the medium where the signal is produced, so the sensitive medium. While sampling calorimeter they alternate layers of absorber with layers of an active medium. The absorber will be typically a very dense material. It could be either lead or tungsten, which will somehow make the electron showering, make the hadrons interacting, and so will degrade the energy, but then the signal will be generated in the active medium. And later we will comment on what are the advantages actually of these different approaches. So, but why calorimeters are so attractive in our field? Well, first of all, as we have discussed, the relative energy resolution is proportional to the 1 over the square root of E, which means it improves when the energy of the particle is larger. So this is not the same as magnet spectrometers, where the momentum resolution gets worse actually at higher energies. And so in this respect, when you go to very high energy, then this is calorimeters are indeed the way to measure the energies. Moreover, calorimeters are sensitive also to neutral particles, because indeed you see the photons, how they produce electromagnetic showers. We will see that, I mean, for hadrons also the neutral hadrons will produce a shower. And well, they could even provide an indirect detection of neutrinos when the energy, the total of the energy is less than what is expected. And they are actually space and cost effective, and the reason of that is that the shower length is proportional to the log, or the logarithmic of your energy. So it means that also the thickness of your detector can increase only logarithmically with the energy. While on the other side, if you have magnetic spectrometers, then the bending power, which is B, the magnetic field strength, times the second power of the length of the magnetized volume, this increases linearly with the particle momentum. So normally, I mean, this is an interesting statement, because normally detecting a particle requires its interaction with the detectors, and neutrinos can actually be directly seen in this way, and this has been described in a previous lecture. But neutrinos can actually also be measured by measuring the missing transverse energy. So if you are sure that there are no other escaping particles, then all the energy which is not visible can be attributed to a neutrino, and then you indirectly see the presence of a neutrino by detecting missing transverse energy. And so, just if we indeed summarize also what happens, we have discussed the longitudinal development of the shower, which is driven by this radiation length. So if you analyze the transverse development of the shower, this is dominated by the multiple Coulomb scattering of low energy electrons, and the scattering formula is given here, and it is indeed given, this is inversely proportional to the momentum of the particle. The angular deviation is inversely proportional to the momentum of the particle, and therefore then if you use this formula, then you end up with the Molière radius, which describes the lateral development of the shower. So this is the typical radius after one radiation length longitudinally, and this is also somehow proportional to the radiation length. And 95% of the energy is within a cylinder of radius which is twice the Molière radius. And this shows the simulation of the longitudinal profile on the left, and you see this is very mildly dependent on the energy, because indeed it goes with the log of the increase only with the log of the energy. And on the transverse shower profile, so this is you see here that this is actually driven by this Molière radius. And so if you assume that there is a thickness of 25 radiation length, then even with an energies up to 300 GeV, then there is only less than 1% of the energy which is beyond, which is left, say, outside or downstream of your detector. So there is a very good containment of the shower with 25 radiation length, even at energies which are very high, and these are the typical energies for the LHC. So that's the end of the first module, and I leave you with this two simple questions which are meant to test that the main messages of these lectures have been actually, you have got the main messages of this first module.